In this video, I want to provide an introduction to unit testing in Python. We'll start by learning about the assert statement, which is the fundamental building block of unit tests. Then we'll talk about what a unit test is, what it's used for, and then we'll see a unit test in action. We will write our own unit test, we'll write the unit, we'll test the unit with the unit test, and make sure that everything is good to go. So let's get started right away. I am in a folder in VS Code called Unit Testing Fun, and all it has is a empty main.py. So I'm going to start by taking some notes in main.py, and then we'll see assert statements in action. So first, what is an assert statement? Well, an assert statement is comprised of the assert keyword, aka reserve word in Python, then a space, and then some expression that evaluates to true or false, meaning it is a Boolean expression, and then optionally a comma and an info message. So recall when you were learning about if statements and while loops, you learned about what are called Boolean expressions. These are expressions that evaluate to true or false. When a Boolean expression is used with an if statement or a while loop, we call it the Boolean condition because it's going to determine some kind of conditional execution, right? Like if the Boolean condition evaluates to true with an if statement, then we take a branch. If it evaluates to false, we don't take that branch. Maybe we test another condition in an elif or an else if, or maybe that's it. We move on to the next line of code outside of the if statement condition. If we're talking about a while loop here, if the Boolean condition evaluates to true, then we continue iterating in a loop. If it evaluates to false, then we break out of the loop and we continue with the next line of code outside of the while loop. So with an assert statement, if the assert expression, the Boolean expression, evaluates to true, then our program is going to continue executing like normal. Okay, interesting. Let's write that down. If the assert statement evaluates to true, then execution continues. It doesn't seem too groundbreaking. The value of the assert statement is what it does when its expression evaluates to false. So if the assert statement's expression evaluates to false, then execution stops. In fact, it doesn't just stop, like hang and wait for input. No. It's going to completely crash your program. It's going to raise an assertion error, and uncaught exceptions will crash your program. Those are runtime exceptions. And oddly enough, this is what you want when you use an assert statement. Assert statements are used for finding bugs in code, debugging those bugs, and fixing the bugs. So if something is wrong, meaning something should evaluate to true but evaluates to false, then when we're testing, we want our code to stop. We want to be able to go see exactly what went wrong. That's the value of the assert statement. It's used for testing our code for functional correctness. Let's see an example. Let's say I want to assert that 3 is equal to 3. Obviously, this evaluates to true. I'll run this. 3 equal to 3 is my expression. It evaluates to true. Looks like nothing happened. But something did happen. Our assert statement allowed our execution of our program to continue beyond line 4. In fact, let's say I print out a little here string on line 5, run the program again, and now I see here proof that line 4 did not crash our program because 5 executed. Okay, let's try asserting that 3 is equal to 4. Well, this evaluates to false. I'll put another print statement in. Perhaps we'll do here and there. And we see here, but we don't see there. In fact, what we see instead is an assertion error. Main.py, line 6, assert 3 equal to 4, assertion error. So we know that 3 equal to 4 evaluates to false. Assert knows at runtime this evaluates to false, so it's going to raise an assertion error, which is not caught. I don't have a try except here. Therefore, my program's going to crash. But I know exactly where it crashes. I've got the module and the line number. I can even provide a little message to help me, the programmer or the debugger, figure out why did this assert statement crash. So perhaps I add a little info message here and say something like testing if 3 equals 4. I can put whatever I want here. This is a string. So now you can see my assertion error is parameterized to include this little info message, which could help me, the programmer / debugger, figure out, okay, what went wrong? How can I fix this? So obviously these two examples of assert statements are not very valuable. We don't need to run the program to know that 3 equals 3 and 3 does not equal 4. But assert statements have a lot of value when we're starting to test more complicated expressions, perhaps expressions where I have some code produced by a function and I have the solution for what should have been produced by that function. Now I have the building blocks for a unit test. Now let's take some notes on unit tests. Generally, a unit test is a function that tests a unit under test, which I'm putting in quotes, for correctness. The unit under test could be a function, a class, a Python module, etc. It's up to you as the programmer to decide what is the unit that you're testing. Typically, the unit that you're testing is a function. So let's write this. Give this definition a little bit more concreteness. Typically, a unit test is a function that tests another function for functional correctness. So recall, a function takes inputs and produces outputs. So given a function under test, we can write a unit test that asserts the function under test produces the correct outputs given certain inputs. And that's the fundamental idea behind a unit test. We have some inputs. We know what the solution output should be. So we run those inputs through the function, and then we assert that the function produces outputs that match what we know are the solution outputs. We assert that. If they're different, crash the program. All right, so how do we do this? So a unit test has one or more test cases. The test cases vary in complexity. So typically you'll start with a very, very simple or common test case. So this could be what's called a happy path through the function. Data comes in, that's pretty common, pretty easy for the function to handle, and it produces a very well-known solution. Then you move on to various test cases of different complexity and edge cases. So then you might think about passing some data into the function that is maybe more complicated or more rare than the simple or common test case. Then you might think about passing in some data to the function that's non-standard, like what happens if you pass in an empty list when it expects a list with some values in it, or what happens if you test a value that's out of range. Maybe your function's only defined for positive numbers. What happens if you pass in a negative number? These kinds of cases. All right, time for an example. Let's pull it all together. So let's write a function that implements the Euclidean distance formula. If you're not sure what the Euclidean distance formula is, absolutely no worries. It is essentially this formula, which is a generalization of the Pythagorean Theorem. I want to use this formula to implement a function because first, we know what some example inputs and outputs are for it. And it has enough complexity that it could be easy to introduce a bug when coding it up. And it's just kind of fun. We've got a square root, we've got a summation, which means we've got a loop, all sorts of fun things. All right, so the Euclidean distance formula here accepts 2 points in Euclidean n space. So when we're talking about Euclidean 2 space, we're talking about 2 points in a Cartesian coordinate system like the grid paper that you're used to. I got an example here, right? Graph paper, grid paper, right? 2 points in 2 space, right? And then it calculates the distance between the 2 points by summing up the paired differences squared and then taking the square root of the sum. So back to 2-space, the Pythagorean Theorem essentially is the hypotenuse between 2 points where the 2 points are connected as legs of a triangle right here. So I thought, since we're all probably familiar with the Pythagorean Theorem, we can implement the Euclidean distance formula, which is just a generalization of 2-space to n-space. So Pythagorean Theorem to Euclidean distance. It'd be kind of fun. And I did this Google search here for distance between 2 points, and I scrolled through the images until I found one that would be a good example. Here's a test case, a very simple test case right here, right? Someone created this image right here that shows an example of distance between 2 points in 2-space. That seems like a pretty simple / common test case, right? We could test that our Euclidean distance formula works in 2-space with this very simple common example right here. So we're going to need a Euclidean distance.py for the function under test. And we're also going to need test underscore Euclidean distance.py for the unit test. I could put both of these functions in main, but that wouldn't be best practice. I'd like to show you best practice, which is you have a module for your unit test. It starts with test underscore, and then it has a name that matches in some shape or form what the purpose of the test module is, which for us will be test in Euclidean distance. And so we'll have a Euclidean distance.py, which is stored separately from the test cases, and that's where we'll put our function. Make one more note here. If we write the unit test before the function under test, then we are practicing what is called test-driven development, or TDD, which is a really great practice. It'll help you implement the function under test if you write the unit test first, because then you have a good notion of what does it mean for this algorithm, this function under test to be correct. If you have to formulate that first, then you're more likely to write that function correctly. Now let's create these two files. So let's start with Euclidean distance.py. And in here, I'm going to have a function called compute Euclidean distance. This will be my function under test. It's going to accept two lists or two tuples of values. I'm going to call these v1 and v2 just to represent that these are two vectors. You can call them whatever you'd like, as long as you're giving them names that kind of indicate that they're lists or vectors. And then in here, I'm just going to do return 0.0 with a to-do here of fix this. We'll come back later and implement the body of this function. For now, it is simply a stub. We've stubbed out this function. Now I'm going to make test Euclidean distance.py. And this is going to be our module that will contain the unit test of compute Euclidean distance, the function, which is in Euclidean distance.py. So I'm going to take a little bit of notes right here at the top, and I'm specifically going to talk about testing frameworks. So using testing frameworks can make executing unit tests nice and easy. The reason why we want to use unit testing frameworks is because if one of our unit tests has an assert statement that fails, it's going to crash the whole program. But we might have other unit tests in the file that don't have any assert statements that fail, meaning those unit tests pass. So we want to run all of the unit tests, even if one somewhere in the beginning or the middle fails. So unit testing frameworks will do that for us. And we have a few options for unit testing frameworks with Python. I think the two most common ones are unit test and Pytest. I will show you how to use Pytest in this video. If you don't have Pytest installed, you may need to pip install it. If you're not sure if you have it installed, then we will find out here in a moment when we go to run it. So with Pytest, modules and functions for testing start with test underscore. So that's why I named this test underscore Euclidean distance.py, because when I go to run Pytest, if I want Pytest to discover all the tests in my project, it's going to look at py files that start with test underscore. And then within those py files, it's going to look for functions that start with test underscore. And it's going to run those functions as if they are unit tests, meaning if they don't crash, then they pass. If they do crash, then it'll give us some indication about why it crashed, perhaps as part of an assert statement message that we provided in our assert statements. All right, so let's write our first unit test. So we're going to write a unit test. So we're going to start it with test underscore and then the name of the function under test, which would be compute Euclidean distance. So in here, we need a really simple, really common test case. And we can grab one from Google. So here's the formula. So right here, if we pass in -2, -2 as one point, one vector, and 2, 6 as another point, another vector, then the distance between the two, as this site here, which I just found on Google, is reporting is 8.94. So that seems like a pretty common, pretty simple test case that we could start out with, especially since it's in two space, and we're all very familiar with the Pythagorean Theorem, which is the Euclidean distance formula in two space. So let's do this one. -2, 2, 2, 6. And then the distance solution should be 8.94. So now I'm going to call compute Euclidean distance. It's in a different file, so I'll need to import it. So from Euclidean distance, import compute Euclidean distance. And let's see what our function returns. I know right now it's always returning 0.0, so this assert statement we're about to write is definitely going to fail, but that's okay. With test-driven development, we write the unit test first, and then we go write the function under test, and then we run our unit test and see if we wrote our function under test correctly. Now, before we write the assert statement, I want to make a little comment. There's a convention for assert statement order, which is actual, meaning the value that was produced, versus expected, meaning the solution. So that means I'm going to write the assert statement as assert distance is equal to distance solution, instead of writing it the other way around. I'm also going to put a to-do in here, which is compare floats in a better way. Distance solution is a floating point number. Distance will be a floating point number. And because they could be really, really, really close, but off by a little bit due to floating point round-off error or just precision issues, I don't want to compare two floating point numbers for equality with the equal sign. I'll show you a better way to do this. Now, let's go ahead and run Pytest. So I'm going to head down to my terminal, and I'm going to run Pytest and press enter. If I don't put anything after the Pytest command, then it is going to, like I said earlier, browse the current working directory and look for any modules that start with test underscore, and then go to those modules and look for any functions that start with test underscore. So it looked like it found one unit test. Perfect. That's what we have, one unit test. Scroll up a little bit here. So test session starts. Here's the one unit test it found, test Euclidean distance. There's an F here for failure. 100% of my unit tests failed, 1 out of 1. And then here's some more information about why it failed. So it looks like right here, test Euclidean distance.py, line 17, assert distance is equal to distance solution. 0.0 is not equal to 8.94. So it failed. Awesome, that's what it should do. Now let's go implement this formula here and then see if it passes. Now would be a good time to pause the video and try to implement this formula. Note that we want to write it generally for n space, which would be the length of v1 and v2, and not just for 2 space, assuming that this is a point in 2-dimensional space with only 2 values in v1 and v2. Try to write it generally. All right, let's go through this. So I'm going to calculate the sum of the squares first. So I'll just use the built-in sum function and sum a list of numbers. The list of numbers would be the difference between each pair of points in v1 and v2. These are parallel. They should be equal in length. Probably should check that. We'll assume they're good though for now. And I'll do v1 sub I minus v2 sub I squared. And now I need to calculate the square root of some squares. So I will import the math module to do this. And I will return math.square root passing in some squares. All right, let's see if our test case passes now. It looks like our solution has more precision than 8.94, which is what was provided in our example here. But it looks really, really, really close. So let's see how we can better compare these two floating point numbers so that close enough is a pass. So to do this, I'm going to import NumPy as NP. NumPy is not a standard Python library, so if you go to run this and you get kind of an error saying that NumPy is not found, then you'll need to pip install NumPy. So I'm going to comment this out, and I'm going to instead use NumPy's isClose function to assert the two values are close. And I'll put in parentheses here, close enough. So let's do assert np.isClose. And I'll hover over it so you can see the documentation. Returns a Boolean array. We're not going to be working with arrays. We'll just be working with single values where two values are equal within a tolerance. The tolerance values are positive, typically very small numbers. So as long as it's close within a very small number, then we say for floating point numbers, they're close enough. So let's do distance, comma, distance solution. And I will run this. Okay, so it's still failing, not close enough. So it looks like maybe I can try changing the tolerance to, let's see, maybe 0.001, and then they should be close enough. Awesome, now it's passing. Okay, so it looks like we have a simple test case passing, but we should probably write a more complicated test case, right? I mean, I had to do a little bit of magic to get this to work, so why don't we write a little more complicated test case, and instead of asserting against what's called a desk calculation, where we calculated what the solution should be by hand, we'll calculate against a library that implements the Euclidean distance function, and we'll see if we can get close, really, really close, not passing in a value for our tall, really, really close to what the library implemented or what the library computed for this function. All right, so I'm going to write a little note here. The above test case was a desk calculation, meaning we test against something that we calculated by hand. We can also test against a validated library implementation. So let's do that. There is a library called SciPy. SciPy has a Euclidean distance function that is tested and correct. We can make sure that our implementation produces a really close value with SciPys. So let's do that. I'm going to scroll up here from scipy.spatial.distance import Euclidean. Hover over this so you can see the documentation real quick. Computes the Euclidean distance between any two 1D arrays. Perfect. That's what we're trying to do. Let's assert our result against Euclidean. So let's make up some more complicated test data. I'm going to seed the random number generator from NumPy so we get reproducible results. Something you almost always want to do in your unit tests so that you're testing the same values every time you run your unit tests. Unless maybe you're testing something random, then you may want to change that. And then let's do v1 is np.random.random, and let's do maybe 10 points between 0.0 and 1.0. Then I'll get the distance solution by calling SciPy's Euclidean, passing in v1, v2, and then I'll get the distance from my function, which is compute Euclidean distance, passing in v1, v2. And then just copy my assert statement and we'll run it for this more complicated test case where instead of a desk calculation, this time I'm going to calculate it and assert it against the Euclidean function from SciPy. So I ran it and it's still passing, which means that we've implemented the Euclidean distance formula well enough that we're matching a validated implementation from the SciPy library. So now from here, I'll leave you with a to-do, which would be come up with additional test cases, perhaps vary the length of v1, v2, maybe try like 1,000 numbers in the vectors, and then perhaps think of some edge cases, right? For example, I said earlier that our Euclidean distance formula assumes that v1 and v2 are of equal length. What if v1 is shorter or longer than v2, right? That could cause some issues. So we should come back to our compute Euclidean distance function and write it more robustly. And our edge cases with test-driven development can help us think about what does it mean for our compute Euclidean distance function to be robust. So there's a hint there. Also, what happens when we pass in empty lists, right? These are the kinds of edge cases that when writing good unit tests, we need to think about because out in the real world, out in production, input is messy and it's often not going to be in the happy little form that we may have written our simple test cases for, like we did here on lines 12 and 13. I'll wrap up by saying that in addition to isClose, NumPy has a function called allClose, which can be really helpful if you are trying to assert that two sequences like NumPy arrays or lists or tuples are equivalent. So you might want to look into that if you're curious. Otherwise, this is a pretty good introduction to writing a unit test, writing a function under test, learning some new terminology, learning some conventions, and learning how to compare floating point numbers. It takes a while to get in the hang of writing unit tests, but they're really valuable. And it also takes a while to get the hang of test-driven development, but that can also be really valuable. There'll come a time where hopefully you'll think, I'm going to write the test for this before I write the function, and that'll save me time overall. And that's kind of a magical moment when you come to that realization and you see the value of test-driven development. That is it for now. Thanks for watching. Consider subscribing to my channel for more Python videos.